Section 23.6. The electronic structure of many electron molecules. In this section, we will look at the shapes of the molecular orbitals of homonuclear diatomic molecules and their molecular orbital diagrams. So first, let's look at the interaction between atomic orbitals. S orbital, S orbital, they can have constructive interference. S orbital, P orbital. In this case, along the bonding axis. This orbital, this P orbital, is anti-symmetric with respect to a symmetry plane that contains this bonding axis, while this S orbital is symmetric with respect to the plane. Therefore, there's no net interaction between this P orbital and this S orbital. And then you can also tell there's constructive interference here, but also destructive interference here. So this is non-bonding. Over here, the P orbital can interact with an S orbital to form a sigma bond. Again, we can look at this bonding axis. Both orbitals, both the P orbital and the S orbital, are symmetric with respect to the symmetry plane that contains the bonding axis. We can assign G and U symmetries to the bonding and antibonding orbitals. This is a sigma bonding orbital. So how do we assign this G or U notation? You draw an arrow that crosses the center of the molecule. And then you look at the sign of the arrowhead and the sign of the arrow tail. If they have the same sign, it's a G symmetry. When they have opposite signs, it's a U symmetry. So that's why in this sigma antibonding orbital, you have a U symmetry with respect to the center of the molecule. Now this is a pi orbital. Is this a bonding or antibonding orbital? Well, clearly we see a planar nodal surface in the middle. So it's a antibonding orbital. Destructive interference between these two lobes. Destructive interference between these two lobes. Now let's draw an arrow that passes the center of the molecule. You can draw from here to here. The sign of the arrowhead is the same as the sign of the arrow tail, or you can just say the colors match. Therefore, it has a G symmetry. So look, this is different. Sigma G is the bonding orbital, but pi G is the anti-bonding orbital. Now let's look at this pi U. Okay, when we draw this arrow, the arrow tail has a blue color, the arrow head has a red color. Therefore, it's a U symmetry. And also, if you look at this shape, it's constructive interference here and here. Therefore, this is a bonding orbital. What about this nodal surface? Well, this nodal surface is not produced in the interaction between the p orbitals. This nodal surface is intrinsic in the atomic p orbitals. Now let's look at the MO diagram of H2 again. So this is the MO diagram of H2. You have one electron here, another electron here. All right, one from each 1s orbital. And then there's two 1s atomic orbitals can form two different linear combinations. The constructive linear combination give you 1 sigma G. The destructive interference will give you 1 sigma U star. So now you put those two electrons in the lower MO over here. The bond order is the number of bonding electrons, 2, minus the number of anti-bonding electrons, 0, and then divided by 2. So the bond order in H2 is 1. Helium. The MO diagram of helium-2 is almost the same as H2, except that you need to put one more electron here, one more electron here. Therefore, this 1 sigma U star is fully occupied. The bond order is 0. This is because 2 minus 2 is 0. 0 divided by 2 is 0. Now let's look at a more complicated case, F2. So in F2, not only the s orbitals interact with each other, we also have 6 p atomic orbitals. 3 here, 3 here. And when the p orbitals interact with each other, there are 2 different ways. I call this head-to-head interaction. And then you have a sigma orbital. So again, if you draw a symmetry plane that contains the bonding axis, you will see this MO is symmetric with respect to that symmetry plane. Over here, these 2 are pi bonding orbitals. This is pi y, this is pi x. Pi y is formed by the 2 py orbitals. This pi x is formed by the 2 px orbitals. All right. And now you're looking at this pi g star and another pi g star in the y direction and in the x direction. They both have a G symmetry. So if you draw an arrow here from negative to negative or from positive to positive, that's a G symmetry. But also you see a nodal plane, okay, that bisects this bonding axis. And you can see clearly the destructive interference between these 2 lobes and destructive interference between these 2 lobes. So that's why those are antibonding orbitals. What about this 3 sigma u star? Well, it's just it looks like this, but you need to swap this plus sign to negative, this negative to positive, and then you should draw a nodal surface in the middle, and that will give you 3 sigma u. Why is this 2 sigma g, 2 sigma u star? Well, not 1. This is because we have 1s orbital below the 2s orbital. The 1s atomic orbitals form 1 sigma g and 1 sigma u star. But because the 1s atomic orbitals are core orbitals, the electrons in the 1s orbitals are core electrons. So chemists do not really care about those core electrons and core orbitals. They are inactive in chemical reactions. So again, this is F2. Now let's look at the order of the energy of these MOs. So 2 sigma g, 2 sigma star, and then over here you have 2pz and 2pz interact to form this sigma g and this sigma u star. All right. So sigma g has a lower energy than 2pz. Sigma u star has higher energy than 2pz. Okay, and this energy increase is greater than this energy decrease. Now pi orbitals. You have 2py, 2px here, 2py and 2px here. The constructive interference will form 2 of these pi bonding orbitals in the y direction and also in the x direction. Over here, you form 2 pi star antibonding orbitals in the y direction and in the x direction. So we call these 2 orbitals degenerate pi orbitals. These 2 are degenerate pi g star orbitals. Now let's look at the bond order. These 2 and these 2 cancel. Now let's look at this picture. We have 6 bonding electrons. You can see these 3 MOs have lower energy than the atomic orbitals. Therefore, they are bonding orbitals. 6 bonding electrons occupy these 3 bonding MO. And we have 4 antibonding antibonding electrons. The bond order is 6 minus 4. You get 2. And then divided by 2, you get 1. So the bond order in fluorine is simply 1. What if you have O2? Well, for O2, you just need to remove 2 electrons. I would remove this beta electron and this beta electron. And then based on the Hund's rule, you will know these 2 alpha electrons, each of them occupy a separate 1 pi g star orbital. So one electron will occupy this orbital. The other electron will occupy this orbital. There are 2 reasons. First, when the 2 electrons occupy these 2 different MOs, that reduces the repulsion between the two electrons. And 2, these two electrons are both alpha electrons, and that help minimize the total energy of the O2 molecule because of the Hund's rule, and also because no two electrons can have the same set of quantum numbers. So two alpha electrons can better avoid each other than one alpha and one beta electrons. That also reduces the repulsion energy between the electrons. So in the O2 case, you have alpha electron here, you have alpha electron here. Well, what if you have one beta here, one beta here? That's the same thing. And that tells us in O2, there are two unpaired electrons with the same spin. Okay, they can both have the alpha spin, they can both have the beta spin. But by convention, we just say they both have the alpha spin. All right, and due to the electron spin, a magnetic moment is produced at the center of the circular electric current. So you have to imagine there are two magnets. And they do not cancel each other because they are both alpha spin or both beta spin. So therefore, O2 is paramagnetic. It can be attracted by the external magnetic field. Now let's look at N2, and similarly B2 and C2. So N2 first. If you look at N2, it looks a lot complicated. You see those dashed lines here? 1, 2 dashed lines, and there's 2 dashed lines, there's 2 dashed lines, there's 2 dashed lines. So first, when you look at the molecular orbital diagram of N2, you see many more lines. This is because this sigma bond is mainly formed by the constructive interference between 2pZ and 2pZ. However, it can be mixed or contaminated by the 2s and 2s. So there's a little bit 2s character in this bonding orbital. So that's why this is slightly distorted from the sigma G in F2. So this is more symmetric, but then when you mix the S character here, well, this lobe is greater than this lobe. This lobe is greater than this lobe. And similarly, if you look at this 2 sigma G, supposedly it's made of 2 s orbitals. So this 2s interact with this 2s, and then you make sigma G. However, because the energy gap between this 2s and 2p is so small in nitrogen, it allows the 2pZ to take part in this MO. And therefore, you can see this 2 sigma G does not look like the interaction of two spheres. And you can clearly see the 2pZ being involved. All right. So, what are the consequences in the order of the energies of the MOs? So you can imagine this sigma G. This is 3 sigma G, and this 2 sigma G. They have the same symmetry along the bonding axis. All right. So basically, these two MOs are symmetric with respect to any symmetry plane that contains the bonding axis. So that's why they can interact with each other. So you can imagine this MO and this MO interact with each other. And what is the consequence of that? When you have two MOs interact with each other or contaminate each other, it will bump the higher energy MO. Okay, so this one was here, and then you bump it up, and then you shift the lower energy MO further down. All right, so in this case, let's get back to fluorine 2. So over here in fluorine 2, the gap between 2s and 2p is so large that there is no interaction between 3 sigma G and 2 sigma G. Now in nitrogen 2, the gap is so small that the interaction between the 3 sigma G and 2 sigma G is so significant that it bumps this 3 sigma G up, and even above the 1 pi u. Okay, so this line is bumped up to above the 1 pi u. This one is bumped down, but it does not change the order of the energy of the MOs. So this one is shifted down. This one is bumped up. All right. So that's why in this picture of N2, this 3 sigma g now lies above the 1 pi u orbitals. What about sigma u star and sigma u star? They also interact with each other. That will bump this down and bump this up. All right, but again, this 2, the interaction between this 2 sigma u star and 3 sigma u star does not change the order of the energies of the MOs. So we don't care about that too much. Really, it's the interaction between 2 sigma g and 3 sigma g that changes the order of the MOs. Those are the pictures of MOs. And again, this is the mostly S-S interaction contaminated by the 2pz-2pz interaction. Same here, it's supposed to be mostly the S-to-S interaction. It's contaminated by the 2pz-2pz interaction. So this one was supposed to be just 2pz-2pz interaction as in fluorine 2, but in this case, because the energy gap between 2s and 2p is so small, it's possible for this 2s to take part in here that make this orbital less symmetric. 3 sigma u star is not drawn here, but it looks similar to this, except you need to change this plus to minus, this minus to plus, and then you need to draw a nodal surface in the middle. Now let's look at the MO diagrams of lithium 2, beryllium 2, boron 2, carbon 2, nitrogen 2, oxygen 2, and fluorine 2. Lithium 2 is just 2 sigma g. Beryllium 2, 2 sigma g, 2 sigma star. So the bond order is 0. 2 bonding electrons minus 2 antibonding electrons, you get 0. And then 0 divided by 2, you still have 0. So really, if you just need to analyze the bond order, you can ignore those 2 sigma g and 2 sigma u star, starting from beryllium 2, because these two cancel, these 2 orbitals cancel, these 2 orbitals cancel, sigma u, sigma g, sigma u star cancel, sigma g, sigma u star cancel, sigma g, sigma u star cancel. Okay. Now boron 2. Boron 2, carbon 2, and nitrogen 2 have similar MO diagrams. So in boron 2, you put 2 electrons in these 2 1 pi u bonding orbitals. Both are alpha electrons, or both are beta electrons, to minimize the energy, to reduce the repulsion between these 2 electrons. So if you look at a boron 2, you just need to get rid of these 2 electrons, and then get rid of this beta electron and this beta electron. You have only 2 alpha electrons that occupy the 1 pi u molecular orbital. So boron 2 is also paramagnetic. Carbon 2. You are looking at carbon 2 if you remove this 2 electrons. That's just carbon 2. The bond order of carbon 2 is 2. And then this is nitrogen 2. Alright, so this is boron 2 with 2 alpha electrons, each occupying a pi u bonding orbital. Carbon 2. The 2 1 pi u bonding orbitals are fully occupied. The bond order is 2. Nitrogen. So we talked about nitrogen. Oxygen. We talked about oxygen. But just a reminder, these 2 orbitals, they are 1 pi g star antibonding orbitals. And you have 2 alpha electrons here. The electron spin of these 2 electrons do not cancel. Therefore, O2 is paramagnetic and it can be attracted in a external magnetic field. Fluorine 2. In fluorine 2, you need to just put 2 more electrons here and here. That's it. That's fluorine 2. The bond order is 1 because you have 6 bonding, 4 antibonding. Take the difference and then divide it by 2. If you are curious about the oxygen molecules being paramagnetic, watch this video. Just do a control click if you have the document. By the way, boron is also paramagnetic, so this is the detailed MO diagram of boron 2. All right. Unfortunately, you sometimes see this as sigma 2G, sigma 2U star. Sometimes it's sigma 1G, sigma 1U star. Or over here, it's just G and U are not even used. It's sigma 1, sigma. So when you see this, just remind yourself, in this MO diagram, the core electrons and the core orbitals are neglected. This is a tricky question. Does carbon-2 have unpaired electrons? No. Okay, so when you have carbon-2, you have 4 electrons in these 2 orbitals. So 2 electrons, 2 paired electrons here, 2 paired electrons here. 1 alpha, 1 beta here, 1 alpha, 1 beta here. And then this C2H6 has a bond order of 1, C2H4 has a bond order of 2, C2H2 has a bond order of 3. It seems you have a trend. When you have more hydrogen atoms, you have a lower bond order. When you have fewer hydrogen atoms, you have a higher bond order. Now, what's the bond order of C2? Well, it's not 4. Okay, if you look at this 1, 2, 3, 4. If you are thinking of 4, you're wrong, and you are not understanding this MO diagram. For carbon-2, you just need to put 1 more electron here and 1 more electron here. Therefore, the bond order is simply 2. You have 4 bonding electrons. I want to show you the actual molecular orbital coefficients obtained from the molecular orbital calculations. You can use different computational chemistry software, such as GAMES or Gaussian, to do the calculations for carbon-2. And in the output file, you will see molecular orbitals in the form of numbers. So I'm going to explain this to you. First, this is just the energy of the MOs. Negative 11 atomic units, negative 11 atomic unit. You see a huge gap here. This is negative 0.9 atomic unit. Why is this a huge gap? They differ by 10 atomic unit. And 1 atomic unit is 2,625.5 kilojoule per mole. So we're talking about 26,000 kilojoule per mole. That's a huge number. A typical chemical bond has a bond energy of maybe 300 kilojoule per mole. And now we're talking about 26,000 kilojoule per mole. So this gap is equivalent to I would say 80 chemical bonds. So it's a huge gap. The reason there is a huge gap here is because these 2 are core orbitals, and this one is valence orbital. And that's also the reason why chemists never care about the core orbitals. They are just too stable. Okay, the core electrons never take part in chemical reactions. So that's the atomic energy. And over here, I want to remind you, in carbon-2, we have 12 electrons. They should occupy the first 6 MOs. 1, 2, 3, 4, 5, 6. All right, and then you can look at this one and this one. These 2 are degenerate orbitals with the same energy. So these 2 are the 1 pi u bonding orbitals. All right. This one is positive, and there's an energy gap here. So this is HOMO, this is LUMO. And now we're going to analyze the numbers. So this one, negative 11 atomic unit, really low energy. The interaction is between 1s and 1s. Constructive interference. Negative 11, okay, look at this. Constructive becomes destructive. Positive 0.7, negative 0.7. But because the distance between this 1s and this 1s is so far away from each other, so really the constructive or destructive interference is minimal. That's why these 2 MOs have a very, very close energy. Now this one, okay, 2s, okay, same sign, they have the same sign. Negative 0.5, negative 0.5, so constructive interference. and then it's contaminated by 2pz and 2pz, 2pz and 2pz. All right, you can see the sign, positive 0.17. This is negative 0.7. Actually, when the signs are different for the 2pz interaction, it's constructive interference. So I want you to just draw 2 2pz orbitals on paper. If they have the same sign, point them to the same direction, and you will see the interaction between these 2pz orbitals is destructive interference. Okay? Because if you have both the positive lobe pointing towards right, okay, and then you look at the interaction between these two orbitals, it's destructive interference. All right, now let's look at this one. Positive sign for the 2s, negative sign for the 2s. Therefore, it's destructive interference between the 2s orbitals. So this orbital is 2 sigma u star. 2 sigma u star. And this is slightly contaminated by the 2pz, so you have 2pz here, 2pz here. This is the destructive interference between the 2pz orbitals. Now you're looking at the 2 degenerate 1 pi u bonding orbital. So I have 0.6 here. This is px interacting with px. Now they have the same sign, but this is the shoulder-to-shoulder interaction. So when they have the same sign, it's constructive. All right, it's constructive interference. 2py and 2py, same sign. This is constructive interference between the 2py and 2py in the shoulder-to-shoulder manner. All right, and then those are unoccupied MOs. We can analyze a few more. So the trick is there are so many numbers, so many coefficients. We look for the larger ones to simplify the analysis. So if you look at this -0.6 over here, all right, 0.6, -0.6, 2pz and 2pz, and over here 2s, both positive. So this is a constructive interference between this 2s and this 2s. This is also a constructive interference between this 2pz and 2pz. All right, and then over here you can see this is just -0.8 from 2py, positive 0.8 from 2py. This is pi g star, another pi g star. All right, I want to show you one final MO. There's a huge gap here, so this should be a very destructive interference. 1.2, -1.2. That's the destructive interference between 2s and 2s. Over here, -1.2, -1.2. Again, this is destructive interference, right? Because it's the shoulder-to-shoulder interaction between the p orbitals. So again, if you draw the p orbitals on paper, okay, and do shoulder-to-shoulder interaction, if they are pointing to the same direction, it's actually destructive interference.